In the previous video, I gave a very abstract introduction to the EM algorithm, the expectation maximization algorithm. But it was sort of unmotivated. I didn't really explain why you might choose to do that particular procedure, for example. So here, why this conditional expectation and why the log of this joint distribution. And for me, at least when I was first trying to understand the EM algorithm, it was very sort of befuddling as to why you would follow this procedure. Why does it sort of make sense and why does it work? So in this video, I want to tell you about a little a way of arriving at the EM algorithm that I recently discovered, and I haven't seen this before. So I think I'm sure somebody's probably found it before, but I think it's kind of neat, and I wanted to show it to you. So remember that the goal in EM is an MLE, or a map estimate. So let's think about the MLE case. So we want to maximize the probability of the marginal distribution, the marginal probability of x. We're maximizing over theta. This is an MLE estimate. And let's specialize to the case of an exponential family. So in general, an exponential family takes the following form. And we're going to think about an exponential family for x and z. The general form of an exponential family is e to the g of theta for some vector valued function g of the parameter theta. The inner product of that with some vector valued function s of x and z times, so it's e to that, times h of x and z for some function h divided by a normalizing constant. And since I use z already, I'm using z already for latent variables. Instead of z for the normalizing constant, let's use c of theta, the partition function. Now, we're trying to maximize this. We're trying to get an MLE, and it turns out that the MLE, or an MLE, satisfies the property that it's invariant under reparameterization. So in fact, it's sufficient to consider only the case where theta equals g of theta. So I'm drawing a picture here to sort of to explain why this is the case. So let's say, so I want to explain why it's sufficient to consider the case of g theta equals theta. And let's suppose that this is sort of theta, where theta lives over here. And let's call g of theta, let's call it eta. Suppose it wasn't equal to theta. So it's eta. And g is a map that takes us from thetas to etas. So maybe we can draw, so this is the set. Let's draw the set of thetas. And then over here is the set of etas, something else. And let's say that this point right here, so my claim is that if we just set g of theta equal to eta and try to maximize this with respect to eta, and we'll have it'll be a different normalizing constant here and all. But if we just try to maximize this with respect to eta, then that's the same thing as if we maximize it with respect to theta. And the reason is because suppose this is a maximizer here over all the possible etas in the range of g, or the image of g. This is the image of g on this set. So this is the image of this set under g over here. And so let's suppose that this point over here goes to there. Well, the question that we want to know is there another theta? Could we have found another theta in this blue set here that would give us a better value? Well, no, because we maximize this over all the etas in the image of g, right? If there were some other point over here for theta, then that would have some image under g, maybe over here, I don't know. But that would be certainly no better than this one because we already maximized over all the points in this set. So that's just a little argument for why it's okay. I just wanted to sort of explain why it's okay for us to assume that this is in natural form. So we will assume that this exponential family is actually in natural form, meaning that g of theta equals theta. And still this is some, it's a funny looking s, let me do that. S of x and z, some vector valued s, and so we have this in natural form. And now we want to maximize this thing. So what is the usual thing we do? Well, the usual thing we do is we differentiate it and set the derivative equal to 0, right? So let's do that. So we will set equal to 0 the derivative of this. Well, okay, well not this, of this, right? We want to maximize the marginal probability of x, so we want to differentiate this with respect to, say, theta I, say the ith coordinate in this vector. And it's equivalent to maximize the log, and usually the log of maximizing the log is a little bit easier. So let's do the log, and this is just, so we can just start differentiating. So we get 1 over p theta of x times the derivative of p theta of x. And let's go ahead and expand p theta of x as the sum. So we'll have the sum of the derivative, sum of the derivatives, over all z's. And now we need to get an expression for this derivative here. So let's make an aside and let's do that. So we want to compute this derivative with respect to theta I of the joint distribution of x and theta. So what is the joint distribution? Let's move it here. Okay, so the joint distribution is this. And let's go ahead actually and let's rewrite this in a little bit different way. We can rewrite this as e to the theta transpose s of x and z. I'll just put s since I'm running out of space. Minus log of c of theta. Right? If we could take, this would be c to the minus 1 if it were in the numerator. And then we could take e of log of that, and we would get e to the minus log c of theta times h of x and z. And so when we differentiate this with respect to theta, this is a constant, and we get the derivative of the exponent with respect to theta I, and the derivative of the exponent is what? Let's see. So we're just going to get the ith component of s here, so we're going to get si of x and z minus the derivative of, let's just keep this, the derivative with respect to theta I of log, that's a funny log c of theta. So we have, that's the derivative of the exponent. And then we keep the original thing. And so we just get this times h of x and z. And that is, of course, just the probability of x and z. And now, so what is this? So we still have to do this derivative of log of c of theta. And it turns out the beautiful thing about exponential families, one of the many beautiful things, is that this, if you go back and look at the videos that we did on exponential families, this, it turns out, equals the expected value under this parameter theta of the ith sufficient statistic. So this is the expectation, and maybe I'll put to distinguish my capital Z's, I'll put little caps on there. So this is the expectation over x and z of the ith sufficient statistic. Remember these s's, these were called the sufficient statistics, each of the different components of this vector valued function s. And this, the derivative of the log, gives you the ith sufficient statistic, the expected value of the ith sufficient statistic. So that's nice. So now we have a nice sort of expression here for this. And let's plug that back in. Let's plug that back in. So I'm going to continue the blue line here. So that was in a side in purple. And now let's continue this blue line. This becomes 1 over, we still have the probability of x hanging out here, sum over z's si of x and z minus this expected value. Let me just I'll drop the parentheses there, times p of theta, p sub theta of x and z. And now if we move this 1 over probability of x and combine it with this guy, then we just get the conditional probability of z given x. And so when we move this, we can move the sum through this difference here, and we will get, what will we get? We get the sum over z si of x and z times the conditional probability of z given x minus, now we have the sum over z of this second part, but this is a constant with respect to z, because this is the expectation over x and the random variable z. So this is not little z here, this is a random variable z. So this is not a function of this little z. And so this is a constant, and we get the sum of the conditional probability of z given x, and that sums to 1 because we're summing over z. So this is just this expected value of the ith sufficient statistic. And what is this part? What is this first part? This is just, maybe I'll keep it in blue for now. This is just the conditional expectation under theta of the ith sufficient statistic x. Now it's just little x and capital Z. Oh, let me put capital X and now condition, because we're going to condition on x. So this is the conditional expectation of this given that capital X equals little x. This is the formula for a conditional expectation when you have a discrete random variable. And so we get the following. Remember we had set this equal to 0 in order to try to get a necessary condition for a critical point of this function with respect to theta, with respect to theta I. And so when we solve here, we move this over to the other side, and we get, so this implies that the conditional expectation of the ith sufficient statistic given x equals little x equals the expectation under theta of the ith sufficient statistic. This is not conditional expectation. This is just the regular old expectation over both random variables, over the joint distribution. So this is a necessary condition for a critical point of theta, for a critical point of that function, of the marginal probability of x as a function of theta. Okay, so I'm out of time in this video. Let me stop there, and we'll continue looking at this, why this is what does this have to do with the expectation maximization algorithm, and we'll see that very shortly.